For over a decade, NVIDIA's CUDA has been the backbone of AI breakthroughs, powering everything from early deep learning models like AlexNet to the latest GPT-4. This dominance is not just about fast hardware, it's about a complete ecosystem, optimized libraries, robust developer tools, and a mature runtime environment. But with this power comes a significant downside: vendor lock-in. CUDA is tightly bound to NVIDIA hardware, and recent licensing changes have made it even harder to run CUDA code on competing chips. For AI labs and enterprises, this means being locked into one vendor's roadmap, pricing, and supply chain. As the AI landscape evolves, the need for alternatives has never been more urgent. CUDA's dominance is rooted in its comprehensive software infrastructure. It offers mature libraries like cuDNN and cuBLAS, advanced developer tools such as profilers and debuggers, and a stable environment that ensures backward compatibility across GPU generations. The ecosystem is further strengthened by extensive documentation, community support, and seamless integration with major AI frameworks like PyTorch and TensorFlow. This maturity has made CUDA the default choice for high-performance AI compute. However, this also means that all optimization efforts are tailored to NVIDIA's architecture, making it difficult for organizations to switch to alternative hardware without significant code rewrites. While CUDA's ecosystem is impressive, it creates strategic vulnerabilities for organizations. Relying solely on NVIDIA means being subject to their pricing, supply chain, and roadmap decisions. Recent licensing restrictions have made it nearly impossible to run CUDA code on non-NVIDIA hardware, further limiting portability. This single-vendor dependency exposes companies to market concentration risks and supply chain disruptions. As Chinese AI labs face export restrictions on NVIDIA hardware, the search for viable alternatives has accelerated, highlighting the urgent need for more open and portable solutions. TileLang emerges as a promising alternative, designed to streamline high-performance kernel development for GPUs, CPUs, and specialized accelerators. With a Pythonic syntax, developers can write kernels as intuitively as they would with NumPy, yet retain low-level control over performance-critical decisions. Built on Apache TVM, TileLang leverages a mature open-source compiler stack, supporting multiple targets like CUDA, HIP, LLVM, and even emerging platforms such as Huawei Ascend. Its just-in-time compilation enables runtime optimization for specific hardware, making it a flexible and powerful tool for modern AI workloads. TileLang operates through a sophisticated lowering pipeline. Developers write high-level kernels using intuitive Python syntax, which are then lowered to TVM's intermediate representation, TensorIR. From there, the compiler generates target-specific code, whether for CUDA, HIP, or LLVM optimized for each platform. Finally, just-in-time compilation produces hardware-specific executables. This architecture enables a true write-once, run-anywhere paradigm, allowing developers to maintain performance competitive with hand-optimized code while enjoying the flexibility of cross-platform deployment. TileLang is designed to accommodate developers at all skill levels. At the library level, users can leverage pre-optimized patterns for common operations like gem and attention mechanisms. For those wanting more control, the developer level allows fine-tuning of tiling strategies, memory placement, and pipelining. Experts can dive even deeper, managing thread primitives, shared memory allocation, and loop scheduling directly. This flexibility means teams can balance productivity and performance optimization according to their specific needs, making TileLang suitable for a wide range of AI projects. At the heart of TileLang's multi-platform capabilities is Apache TVM, a production-grade compiler framework built for hardware diversity. TVM abstracts, loops, threads, memory hierarchies, and specialized instructions using TensorIR. It systematically applies scheduling transformations like loop tiling, vectorization, and fusion, and even includes auto-tuning to find the most performant configurations. With back-end flexibility, TVM supports everything from data center GPUs to edge devices, transforming portable kernel descriptions into efficient, hardware-specific implementations without sacrificing maintainability. The DeepSeek V3.2 experimental release offers compelling proof that the TileLang plus TVM approach works at scale. This model, shipped with simultaneous deployment paths for Huawei Ascend NPUs, Cambricon MLUs, Hygon DCUs, and NVIDIA GPUs, Each platform received optimized kernels, demonstrating that frontier AI models can run efficiently on non-NVIDIA hardware from day one. This wasn't just a research experiment, it was a production-ready release, signaling a new era of hardware independence for AI. DeepSeek's approach combines the best of both worlds. On one hand, FlashMLA provides hand-tuned CUDA kernels for maximum performance on NVIDIA hardware. On the other, TileLang generates portable, compiler-optimized kernels for deployment across diverse platforms. This strategic pairing allows organizations to maintain competitive performance while building hardware independence, ensuring flexibility and resilience in a rapidly changing AI hardware landscape. One of the most striking achievements of TileLang is its ability to match the performance of hand-optimized CUDA kernels with just 80 lines of Python code. Benchmarks show TileLang achieving near parity on matrix multiplication, GEM, across NVIDIA and AMD GPUs, as well as on specialized operations like flash attention and dequantization GEM. This consistency across diverse operations and hardware platforms is a testament to the maturity of the TileLang compiler stack. While TileLang delivers impressive performance, it does introduce a compilation time trade-off due to just-in-time JIT compilation. This can add some startup latency, especially for large models. However, recent improvements like NVRTC backend integration have significantly reduced these times, making TileLang practical for production deployments. For many organizations, the slight delay is a small price to pay for the flexibility and portability TileLang offers. The rise of TileLang and TVM has significant strategic implications, especially in the context of U.S. export restrictions on advanced chips to China. DeepSeek's V3.2 release, with simultaneous support for Chinese accelerators, signals a coordinated effort to build a complete indigenous AI infrastructure. TileLang, developed by researchers at Peking University and Microsoft Research, is not just a technical innovation, it's a step towards strategic independence and resilience for the global AI industry. Perhaps the most important impact of TileLang plus TVM is the return to open, portable ecosystems. Developers can now write kernels once and deploy them everywhere, invest in skills that transfer across platforms, and contribute to community-driven optimization. This flexibility is similar to the software containerization revolution, abstracting away hardware differences while maintaining high performance. As hardware markets evolve, this open approach ensures that codebases remain adaptable and future-proof. TileLang is a strong candidate for teams deploying across multiple hardware platforms, organizations facing NVIDIA supply constraints, research labs experimenting with custom accelerators, and cost-sensitive applications where hardware flexibility matters. It's also ideal for long-term projects that want to future-proof against vendor lock-in. However, if your operations are exclusively on NVIDIA hardware, require every last bit of performance, or rely on highly specialized CUDA operations, sticking with CUDA may still be the best choice for now. CUDA's dominance was built on first-mover advantage, sustained investment, and network effects, not just technical superiority, but monopolies rarely last forever, especially in technology. TileLang plus TVM represents the most credible challenge to CUDA's hegemony in over a decade, combining Pythonic productivity, compiler sophistication, and multi-platform performance. DeepSeek's V3.2 release proved that open, portable infrastructure can deliver competitive AI performance. For the industry, this shift means liberation from vendor lock-in, faster hardware innovation, and democratized high-performance computing. The future of AI compute is open, flexible, and rapidly evolving.